Namaste and welcome to week 8 of this lecture series on mathematical foundations for machine learning. The first 4 weeks we focused on linear algebra. We looked at the idea of vector spaces, then we looked at bases, we looked at dimension subspaces, and then we looked at the idea of orthogonality, then we looked at linear transformations, we looked at eigenvalues, eigenvectors, and then we did singular value decomposition and so on. Week 5 onwards we started doing probability. We just had the basics of probability in week 5, followed by random variables, and then multiple random variables. We had joint expectations and other things. We are in the last week of probability and statistics related ideas, and from week 9 onwards we will look at calculus, multivariate calculus, and then applications and so on. In this week 9, we are going to look at a few interesting topics. The first one, we are going to look at some inequalities, or let us say some probabilistic inequalities. The next thing we will be looking at the idea of limit theorems, which is basically where we are going to look at central limit theorem. This is most extensively used in statistics, where you say that look, the distribution of the population parameter could be anything, but then when you do sampling from this population, the sample statistics will have a distribution if which is normal distribution, provided the sample size is fairly large, and we will be looking at that. And then we will look at the one of the most important ideas of, let us say, covariance matrix. We are going to, it is here that we are going to bring in the ideas of vector spaces, especially the idea of real symmetric matrices, to help us out in studying covariance matrices. So we are going to look at covariance matrices. Let me make this as 4. Prior to this, we want to bring in the geometric aspect. So after this, it will be good to study the covariance matrix. So we want to bring the geometric aspect of sample. First of all, we should know what a sample is. In statistics, sample makes a very, that is a term that is used a lot. So we want to look at samples. What is it to say a sample? What is the geometry of a sample? What does it convey? All those things we will be studying. So we will be studying sample geometry, followed by computation of the covariance matrices. And I remember saying, even when we did real symmetric matrices, we said that look, something interesting is coming up about the real symmetric matrices, the ideas of real symmetric matrix, and that we will study when we do covariance matrices. So we will be studying covariance matrices extensively in this particular week's lecture, and then we will conclude the idea of probability and statistics before we embark on a journey on calculus, multivariate calculus. We will look at gradient. What does this gradient descent algorithm actually mean? Everybody talks about gradient descent algorithm and so on. So we will look at what does it actually mean, and then we will look at some applications of all these ideas that we have done. Maybe we will do a little bit of neural networks, we will do perceptron, and then we will look at some regression, ideas of regressions and so on. In the next the beginning week, in week 10, 11 and 12, we will be looking at that, where Dr. Ashok Rao will be giving the lectures. So let us get on with this week's topics. which is some probabilistic inequalities. That is the first one that we are going to look at, followed by limit theorems. Let us look at what does this probabilistic inequality mean. What do we mean? Why do we even study this? What is the significance of inequalities and stuff? The first thing that we will do is, let us do a quick recall. What is it that we want to recall? Recall the idea of cumulative distribution function, the cumulative distribution function, or the CDF. CDF given denoted by capital letter F sub x of x. And how did we say this? Uppercase f x of x, which is probability, the cumulative distribution function, as the probability of the random variable taking x taking a value at most x. It is going to take a value which is at the maximum going to be x. So, what is the probability of the random variable x taking a value which is at most x, right. In fact, we actually understood that this is also a very good this is also another probability model for the random variable x in the absence of our probability mass function or the probability density function. In fact, we also saw that you either have probability mass function or you have probability density function. I mean, we said that probability mass function may be defined, may not be defined, probability density function may be defined, may not be defined, but cumulative distribution function is always there. We also made the statement. So, now what we want to do is we want to look at this CDF, we just want to understand what this means, and then we want to go for our probabilistic inequalities. Now, if you look at this expression that we have written here, which says f x of x is equal to p of x less than or equal to x, what we are trying to say is, look, I put a threshold at, let us say x, or let us say I will change this to, let us say k. F x of k is nothing but probability that the random variable x takes a value less than or equal to k, that means at most k. So, what do we mean by this at most k? It is like this. So, I have my random variable x and here I have the value k. Now, what I am going to ask is, I am going to ask this question, what is p of x less than or equal to k? This is basically my f x of k, right. For all the values less than or equal to k, I am going to get probability of x taking value at most k to be f x of k, the cumulative distribution function. But not at all times I will be interested in this, but I will be interested in what is the probability that the random variable takes a value beyond k. That means, what is the probability that the random value or a random variable x takes a value which is at least k. That means, I am setting a threshold here. So, what I am going to do is, I want to look at this, I basically want to look at what is the probability of x taking a value greater than or equal to or greater than k. So, I want to look at p of x greater than k, right. You can also say, okay, p of x greater than or equal to k. P of x greater than k is 1 minus p of x less than or equal to k, that is easy to do, but what we want is p of x greater than or equal to k. So, what are we looking for? We are interested in finding out, or we are interested in knowing the probability that x, that the random variable x takes value at least k. When I say at most k, this is basically probability of x taking a value at most k. Now what are we looking for? We are looking for probability that the random variable x takes the value at least k. That means I am going to look at, I want to find out, I want to compute this probability. Now what do we mean by this probability? Why do we even want to look at this? Let us take a simple example. Say I have my Gaussian distribution, let us say I have this Gaussian distribution which is here. I want to find out what is the probability of this random variable x, let us say taking a value greater than or equal to k, where k is a value that I fix here. That means I want to look at this probability. That probability is going to be extremely small, is what we see here, right. At least in the given case we find that this probability is going to be extremely small, because probability here in this case is going to be the area under the curve. The area under the curve is basically area under the curve beyond x is equal to k, right. Now why do I want to compute this? This probability that I compute is basically called as the tail probability. So I want to study the tail probability distribution. So what we want to do is by looking at p of x greater than or equal to k, we basically want to study the tail probabilities or the tail probability distribution. We basically want to look at the tail probability distribution of this random variable x, right. Okay. Remember, a very important stuff that we want to have, a very subtle point that we want to mention here is, when we had this what would you call again remember or recall the property of cumulative distribution function. What is that? Probability of x less than or equal to infinity is nothing but fx of infinity, which is equal to 1, right. That is a property that we said. So what is it to say probability of x less than or equal to infinity? It means you are looking at infinity is the maximum number that you can have, and all the values of x will be less than or equal to infinity. Therefore it is the probability of the sample space itself. So it is going to be the what would you call, that is a sure shot event, that is a certain event, and therefore the probability is going to be 1. Now what happens is, if I keep my k larger, if the value of k is larger, so from here we understand that, okay, let us do this. So if k is larger, the probability p of x greater than or equal to k tends to go smaller and smaller, tends to become smaller and smaller. Why does it become smaller and smaller? Because we know that as k approaches infinity, we know that p of x less than or equal to k is 1. Therefore the value which is, let us say the value of k, if it is very close to infinity, p of x greater than or equal to k would be very small value, right. So this is something which we have in mind. This is as a result of our understanding of cumulative distribution function. Now what we want to do is, we want to estimate, let us do this, we want to estimate how small is this probability for large values of k. We want to look at we want to estimate how small this probability is for large values of k. Let us take a simple example and then try to understand this problem, right. Consider the following example. So, what we do is we are going to look at this, let x be a random variable that models the, let us say, height of 100 students in a class, 100 students in a class, and let us say the height is measured in centimeters. So, let us have this condition also, let the average height of the class be let us say 160 centimeters. Now, what are we going to do? We want to estimate the probability that a randomly chosen student student's height is at least, let us say 180 centimeters, right. That means, what are we going to ask? That means, in a sense, we are looking at probability of x greater than or equal to 180 centimeter, right. We want to estimate this probability, we do not even know what the distribution is. All that we are given is, look, x is a random variable which models the height of 100 students in a class, and the average height of the class is 160 centimeters. I randomly pick a student from this class, I ask what is the probability that this fellow's height is 180 centimeters, at least 180 centimeters, not exactly, it is at least 180 centimeters, that it could be beyond that also, right. So, how do we compute this probability? How do we get this estimate? We may not get an accurate value, but we want to estimate it, which is typically what we do, right. We do an estimation, like when we say I want to go from this place to that place, we try to estimate what is the time that it takes, it could take, right. In all probability you might actually reach a bit earlier, but there is a slight chance that you may actually get stuck in traffic and you might travel a bit late. So, we want to estimate that probability, we just want to make an estimation. Okay. So, how do we solve this problem? Let us take let us try to solve this problem and try to understand what we are trying to do, right. Okay. So, now what I am going to do is I am going to take this, I am going to divide this class of 100 students that I have into 2 classes, right, into 2 classes. I do not even know what is the distribution. So, I am just going to say I am going to distribute into 2 classes. One class is the set of students whose height is, let us say, greater than or equal to 180 centimeters, and the other class is less than whose height is less than 180 centimeter, right. I am going to do this. So, what I am going to do is, and I am also going to make a statement that let k be the number of students whose height is at least 180 centimeters. Therefore, we have 100 minus k students in the remaining class, right. So, let us write this, let k be the number of students let us say whose height is at least 180 centimeters, right. So, in a class of 100 students, so therefore, we have already made two groups of students where in which one group the minimum height is 180 centimeters and the number of students there is k, and another group where the height is less than 180 centimeters. Therefore, we have number of students to be 100 minus k. Is that clear? So, we have, let me call this as group A and let me call this as group B, right. I have this. Now, what I am going to do is I want to find out what is the total height of the class. So, total height of the class is basically you cannot the total height of the class, you know what it is. You are given the average, you know the number of students who are there in the class, which is 100. Therefore, the total height of the class is nothing but 100 into the number of students into the average of the class, average height of the class. So, this is nothing but number of students into this is equal to number of students into average height. Right, and what is that number? That is basically given by this is nothing but 100 into 160. So, we have okay, let us just keep it as 100 into 160. Now, what is the total height in group A? Total height in group A. What is the total height in group A? That is nothing but number of students into 180, right, number of students into 180, which is nothing but k into 180, right. Okay. Now, what is the therefore, what we know is we know that the total height of the class is greater than or equal to the total height in group A. The total height in group A, right. Now, what do we mean by this? We have the following. So, what it means? It says 100 into 160, that is the total height of the class, is greater than or equal to 180 into k, right. 100 by 100 into 160 is greater than or equal to 100 into k. So, what do we have here? I can write this as, therefore, 180 into k is less than or equal to 100 into 160. Is this right? We have this, which implies k divided by 100 is less than or equal to 160 by 180. Is this correct? 180 into k is less than or equal to this. So, k divided by 100 is less than or equal to 160 divided by 180. Now, if you cross multiply this, you get this k into 180 is less than or equal to 100 into 160. So, this is what happens. Now, you see something interesting happening here. What is that? What is k by 100? 100 is the total number of students. K is the number of students whose height is at least 180 centimeters. Therefore, what does k by 100 give you? K by 100 gives you the probability that the probability of the students being greater than or equal to 180 centimeters in height, right. This is nothing but number of students in group A, number of students in group A divided by total number of students is less than or equal to 160 divided by 180. Number of students in group A divided by total number of students is nothing but the probability of k greater than or equal to 180 centimeters is less than or equal to 160 by 180. Is this correct? 160 by 180. Now, what is 160? 160 is the average height of the students in the class. When we say average height of the students in the class, it actually is the expected value of x. The mean height, it is going to be expected value of x. So, what I am going to do is I am going to say p of k greater than or equal to 180 is less than or equal to expected value of x, which is the mean divided by k, right, divided by k. So, we will say this divided by 180 here in this case. Oh, this is not k, sorry, this is a mistake, this is height being greater than or equal to 180, sorry. This is height greater than or equal to 180, this is height greater than or equal to 180. Now, the height is basically modeled by the random variable x. So, I would say p of x greater than or equal to 180 is less than or equal to expected value of x, that is the average value of height divided by 180. Is this right? I will write this here, this is 160. Now, I will bring that notion expected value of x by 180, right. So, what do we have? Suppose I have a threshold k. What does this mean? This implies probability of x greater than or equal to a threshold k is less than or equal to expected value of x divided by k, provided k not equal to 0, right. And this expression that we have here, p of x greater than or equal to k is less than or equal to expected value of x by k, this is what we call as the Markov inequality. Markov inequality, right. It says the probability that the random variable x takes at least a value k is given by is less than or equal to the expected value of the random variable divided by the threshold that you have set, threshold is that k, right. So, let us formally state the Markov inequality. We are going to do this. Now, note one important stuff here, the random variable x was measuring height and that height can never go negative. So, what we say is x is basically a random variable which is non-negative random variable. So, we are going to say for any non-negative random variable x, for any non-negative random variable x, with mean, we will write in bracket finite expectation, expected value of x is finite, E of x which is finite, and any threshold k greater than 0, the probability of x greater than or equal to k is less than or equal to expected value of x divided by k, right. And what is interesting is this particular inequality does not depend on the distribution of x. I do not care what is the distribution of x except the fact that x has to be a non-negative random variable. I do not want to know what is the underlying distribution, probability distribution of x. What I am looking for is probability of x greater than or equal to k is less than or equal to the expected value of x by k, where expected value of x must be finite. Is that okay? So, that is basically what Markov inequality says. That means there is a small catch here. What is that? This Markov inequality is not applicable to a random variable which takes negative values. It is applicable only to set of values which are it is applicable only to those random variables which are non-negative, say probably binomial distribution, probably Bernoulli, geometric distribution, Poisson distribution, and so on. It is not applicable to any random variable which takes negative values, right. Okay. Let us see if we can understand this better. Like I am not getting into the proof of this, but at least this example gave us an idea about what this inequality is all about. So, we are basically looking for conceptual understanding. So, I would skip the proof in this case. The proof is pretty simple to work out, but then I would skip here because I want to continue with the other inequality. I also want to look at certain examples here, right. Okay, fine. So, now what we will do is let us take a simple case. What are we going to do? We will look at certain examples and see what happens if you use Markov inequality to, let us say make an estimate of this probability, tail probability. Okay. So, what I am going to do? I am going to look at this first question. First thing that I want to do is, suppose I have a biased coin, with probability of tossing or with probability of head. Is equal to 1 by 5, probability of head being 1 by 5 is tossed 10 times. So, the question is estimate the probability of getting at least 8 heads. At least let us say 8 hits, right. Now, let us try to use Markov inequality and see what happens. Let us look at the normal way of computing the probability based on binomial distribution and see what happens. Now, if I use Markov inequality, I have to find out what is the expected value of x. Expected value of x in this case is n into p, where n is 10 and probability is 1 by 5. So, expected value of x is 2. So, by Markov inequality, what do we have? By Markov inequality, we have p of x greater than or equal to 8 is less than or equal to expected value of x divided by 8. That means p of x greater than or equal to 8 is less than or equal to 2 by 8, which is 1 by 4, which is 0.25. So, this is the number that we get. So, what is so great about this number? Now, let us see what happens if I do it in the normal binomial distribution way, where I have P of x greater than or equal to 8 is given by sigma k is equal to 8 to 10. What do we have? We have 10 choose k, and the probability of success is 1 by 5, 1 by 5 power k into 4 by 5 power 10 minus k. This is what we have. Now, if you substitute the value of k here and then compute this probability turns out to be a number which is like this 0.00000779. Oh, this is pretty interesting. The actual probability of x greater than or equal to 8, that means the actual probability of number of tosses, number of heads being greater than or equal to 8 is extremely small, but our Markov inequality gave an estimate which is like quite large compared to this, right. That means Markov inequality gives some kind of an exaggerated estimate for this tail probability. So, that is the first understanding that we have. So, Markov inequality gives exaggerated estimate right, it gives exaggerated estimate. Now, let us look at, let us ask this question in that case. Oh, it gives exaggerated estimate, does that mean this Markov inequality is useless because it gives so much, the estimate is so much exaggerated compared to the value 1 by 4 0.25, this number is extremely small. So, why do we use this? Does this inequality give exact answer at any point of time? We have used less than or equal to, P of x greater than or equal to k is less than or equal to expected value of x by k. That means, does it actually give a bound which is exactly equal to E of x by k at any point of time? If not, I mean this does not, this entire exercise is futile. Like, so question is, does it give a bound which is like equal to like the E of x by k. So, what is that? So, we are going to have, does the Markov inequality at any point of time. So, does the Markov inequality at any point of time give exact probability value that is the Markov inequality, or we say, can the Markov inequality give an exact estimate, exact probability, give the exact probability. Or the actual probability, let us say, can give the actual probability, that makes it better, right. Can the Markov inequality give an actual, the actual probability at any for any case, that is what we are going to look at. Now, what we will do is let us look at this probability mass function, example 2. So, we look at this probability mass function where x is the random variable with PMF, Px of x is equal to 1 by 25 whenever x takes the value 5, 24 by 25 whenever x takes the value, let us say 0. So, what is the probability I want to ask? I want to look at what is probability of x greater than or equal to 5. Now, we know that this is a binomial random, this is a Bernoulli random variable which takes just two values and you have this probability values to be 1 by 25 and 24 by 25. So, let us look at what is expected value of x. Expected value of x is 5 into 1 by 25 plus 0 into 24 by 25, which is basically 5 into 1 by 25, which is 1 by 5. Now, if you apply Markov inequality, so we will see using Markov inequality, we have P of x greater than or equal to 5 is less than or equal to expected value of x by 5, expected value of x is, so what do we have, expected value of x is nothing but 1 by 5 and this is divided by 5, which is nothing but 1 by 25, and that is the exact probability that we have. So, Markov inequality can also give the actual probability without exaggerating, right. So, that is basically seen through these two examples. Let us take one more example to understand how Markov inequality can also give some senseless number, right, how it can give some what do you call some stupid numbers. Let us look at this. Say for example, I have a fair die. So, we have example 3. So, I am going to look at this example where x denotes, x is a random variable that denotes the face that comes up when we roll fair 6 sided die. So, x is going to take values which are 1, 2, 3, 4, 5, 6, 1 among this, and therefore, I am going to look at the PMF of x, the probability mass function of x, which is given by Px of x. Since we said a fair 6 sided die, each of those numbers have the same probability as every other number. So, I am going to take this as 1 by 6, x is equal to 1 to 6 and 0 otherwise. Now, I am going to ask this question, what is the probability of x taking a value which is at least 3, right, probability that x takes a value which is at least 3. So, now what we do is let us apply Markov inequality here, Markov inequality. So, when I apply Markov inequality, what do I get? I get P of x greater than or equal to 3 is less than or equal to expected value of x divided by 3. Now, what is the expected value of x in this case? Expected value of x in this case is 1 by 6 into 1 plus 1 by 6 into 2 plus etcetera plus 1 by 6 into 6, right, which is basically what do we get here? We get 2 plus 2 4. So, you basically get, you compute this 4 plus 3 6, 4 plus 3 7, 7 plus 4 is 11, 11 plus, okay, let us do that. So, I have 1 by 6 plus 2 by 6 plus 3 by 6 plus 4 by 6 plus 5 by 6 plus 6 by 6. So, this is going to be 1 plus 2 3 plus 3 6 plus 4 10 plus 11 is 21. So, I am going to have 21 by 6 which is 3.5, right, that is my expected value of x. Now, you plug that value here, what do we see here? P of x greater than or equal to 3 is less than or equal to 3.5 by 3. This is an absurd number because we know that the probability cannot exceed 1, and what is the estimate that it gives? It says it is almost, I mean, P of x greater than or equal to 3 is less than or equal to almost 1.2, it does not make sense. So, you will get some numbers like this also with Markov inequality. So, the question that we are going to ask now is, if I have Markov inequality which is giving me exaggerated bounds at some times, some bounds which do not even make sense at times, can we make the bound tighter? Is there something else that we can do to make the bound tighter? That means make it a bit sensible, and here we saw this bound was for the previous example, where was 0.25 and where was the number that we wrote. So, can we make it a bit tighter? If that is the case, what is it that one more parameter that we would want so that the bound actually makes sense and it gives a better estimate compared to Markov inequality? And that is exactly where we are going to study Chebyshev inequality, and Chebyshev inequality will form the topic of discussion for the next class, where in which we will also look at Chebyshev inequality and we will probably get into the idea of central limit theorem. So, in this class what we have done, we were looking at estimating tail probabilities. We are interested in tail probability because we want to get some bound for our random variable going beyond certain value, and when the random variable was a non-negative random variable, we figured out that Markov inequality, whatever that we had done, say Markov inequality for a random variable with a finite mean or expected value, gives a bound which says probability of x greater than or equal to any non-zero threshold is less than or equal to expected value of the random variable x divided by the threshold that we have set. But this threshold, this estimate that we get seems to be quite we would not say inconsistent. At some point it gives exaggerated, at some point times it gives equal, at some point of times it actually makes no sense. So, we want to see some sensible estimate of this tail probability, and in order to get a sensible estimate of this tail probability, we will study what is called, we will look at what is called as Chebyshev inequality, and that will be the topic of discussion for the next class. Namaste.